Particles in stable or unstable equilibrium. A particle of mass 3m is located delta x equals 1.00 meters from a particle of mass m. Part A. Where should you put a third mass capital M so that the net gravitational force on capital M due to the two masses is exactly zero? Part B. Is the equilibrium of this capital M at this point stable or unstable? For the first scenario, for points along the line connecting M and 3M, and second scenario for points along the line passing through capital M and perpendicular to the line connecting M and 3M. So here is the situation. We have M and 3M at a distance delta x from each other. We're placing another mass capital M in between them. At a certain location, a distance x from M, a distance delta x minus x from 3M, such that the net force on capital M, gravitational force on capital M, is zero. So where is this location? So the force applied by M on capital M, the gravitational force, attractive force, is the universal gravitational constant G, M, capital M, divided by the distance between them, x squared, and this is pointing in minus I hat direction, as you can see here. It's an attractive force. The force applied by 3m on capital M is G 3m capital M divided by delta x minus x squared. That's the distance between them. And it is in plus I hat direction. Once again, this is also an attractive force. It's attracted towards 3m. Okay, so what is the net gravitational force acting on capital M? Net force is force applied by M on capital M plus force applied by 3m on capital M. The first one was minus G M capital M over x squared in I hat direction. The second force is plus G 3m capital M divided by delta x minus x squared in I hat direction, and this must be equal to 0. So I see that g's will cancel and I will get rid of m capital M products here. So this will give me an equation minus 1 over x squared plus 3 over delta x minus x squared is equal to 0. So this is equilibrium. So I find that 1 over x squared, if I take it to the right hand side, is equal to 3 over delta x minus x parentheses squared. So delta x minus x parentheses squared is equal to 3x squared, which tells me delta x minus x is plus or minus square root 3x. So in x parentheses, this is x times 1 plus or minus square root 3 is equal to delta x. So which one should I take? The first one, x1, possible root, is 0.366 delta x for 1 plus square root 3. And the second one, the minus root, is x2, is minus 1.366 delta x. Now, for this force to be in this direction, pointing in minus I hat and plus I hat, it has to be in between these two masses, so it cannot be outside this region. So I see that x must be less than delta x. Therefore, this is not a physical solution. So this cannot be considered. So we find that the position of capital M is x equals delta x divided by 1 plus square root 3. And for delta x equals 1 meter, this corresponds to an x value 0.366 meter. So capital M must be placed at a distance of 0.366 meters from M and 0.634 meters from 3M. All right, and now we're going to investigate if this equilibrium is stable or unstable. All right, so in part B, the first scenario, what happens if capital M is displaced a small distance delta x to the left towards a mass M. So let's say that it's displaced by delta x towards mass M. So what will happen to the net force? It will be now G M capital M. Now the distance between them has decreased, x minus delta x squared in I hat direction, plus in minus I hat direction, plus G M3M, M3M capital M. Now it was delta x minus x, now it is delta x minus del x squared in plus I hat direction. So what do I see? The force between M and capital M magnitude increases because the denominator decreased here. And on the other hand, so it was 0.366, now it's something smaller, the force has increased. What happens to the force between 3M and capital M? It was delta x minus x. Now it is displaced by a distance delta x to the left. So this actually becomes delta x minus x plus del x, not minus del x. So we have to be careful. If this is displaced by an amount delta x, this is going to become delta x minus x plus delta x. That will be the new distance between them. So this is going to be plus, but this is minus. So Fm capital M increases, but in this case, because the denominator has increased for the second term, the force 3M capital M decreases in magnitude. So what does that mean? So that the net force will not be zero, it will be in minus I hat direction towards mass M. All right. Now, if capital M is displaced a small distance delta x to the right, what happens? The net force, F net, now I'm increasing the distance between M and capital M, will become Gm capital M divided by x plus delta x squared in minus I hat direction. And for the force between 3m and capital M plus G 3m capital M, now I'm decreasing the distance between them from delta x minus x to delta x minus delta x, since it approached by an amount delta x to mass 3m. So what do I see? In this case, the force between m and capital M decreases because the denominator has increased, but the force between 3m and capital M increases because the denominator has decreased. So this implies that in this scenario, the net force will be in plus I hat direction towards mass 3m. So what do I see? In either case, if I displace it by a small amount, since the net force does not point towards the equilibrium point, the system doesn't try to reach the equilibrium back again. The equilibrium we establish in this situation is unstable. All right. Second scenario. Now I see that this mass capital M is displaced perpendicular to the line connecting M and 3M. Since for the x component of the force here, because the distance between M and capital M and capital M and 3M doesn't change, the x components will remain the same, but the y components will change, and there will be, the x components will still cancel, but the y components will add up and point towards the equilibrium point for displacements upwards or downwards. So I will see that the system tries to go back to the equilibrium point again. So if capital M is displaced on a line perpendicular to the line connecting M and 3M, since the x components of the forces, force between M and capital M and force between 3M and capital M do not change, there is no net force on the x-axis. This is still valid. And the net force, F net, points towards the equilibrium point. So as soon as I destroy the equilibrium by moving this mass on a line perpendicular to the line connecting the two masses, that is on the y-axis, it tries to re-establish equilibrium. So the system tries to go back to equilibrium again. So the equilibrium in this case is stable. So for displacements on the y-axis, this is a stable equilibrium. So let's see what we have done. We have put two particles, mass 3m and m, at a distance 1 meter from each other. We're inserting a third particle, mass capital M, such that the net force on this particle is zero. Equilibrium is established. It is located at a distance x with respect to m and at a distance delta x minus x with respect to 3m. By writing the gravitational force between m and 3m and noting that it is attractive, gm capital M over x squared minus I hat, it's pointing towards m and it scales as 1 over the distance between them squared. And the force applied by 3m on capital M is g 3m capital M over delta x minus x squared in I hat direction pointing towards 3m. Setting this equal to 0, we find two roots. The x value is either delta x divided by 1 plus square root 3 or 1 minus square root 3. 1 plus square root 3 gives me 0.366 delta x. 1 minus square root 3 gives me minus 1.366 delta x. But for this scenario to hold, it must be between m and 3m, so the negative roots should be ignored. The answer is delta x divided by 1 plus square root 3. As for the given numerical value, it is 0.366 meters away from m and 0.634 meters away from 3m. Now, is this equilibrium stable? How do I find out? I displace it by a small amount to the right or to the left. If I displace it by a small amount delta x to the left, that will decrease the distance between m and capital M. Therefore, the magnitude of this force will increase. So it will be attracted more towards m. And at the same time, because this will be increasing the distance from delta x minus x to delta x plus del x, as you can see here, this force will decrease, this force increases, so it will start moving towards mass m. If I do the opposite, if it moves towards mass 3m at a distance delta x, the distance between capital M and 3m decreases, the force 3m capital M increases, and the force m capital M decreases because now it's at a higher distance from m. And therefore it will be attracted towards 3m, start moving towards 3m. In either case, it doesn't try to go back to the equilibrium point, therefore the equilibrium is unstable. If I displace it on the y-axis, I see that because the x component of the two forces, Fmm and F3mm, is basically going to be the same because the position vector x components doesn't change. The x components of these forces cancel, but the y components add up vectorially. You can see that they point towards the equilibrium point. Therefore, by displacing it by a small amount, net force on the x-axis is 0, but the net force points towards the equilibrium point. The system tries to go back to equilibrium. Therefore, the equilibrium established in this case is stable.